Hello students, in the previous class we have seen the valence bond theory. In valence bond theory we have spoken about covalent bond, means sharing of electrons we have spoken, but it could not explain the unshared pair of electrons properly. So by taking the limitation of valence bond theory, today we are going to explain about the crystal field theory. So here in crystal field theory mainly explains about stabilization of the electrons and color, geometry, and also degenerate orbitals. Degenerate orbitals is nothing but same energy. Means what means here, the crystal field theory depends upon the complex ions, we can say. Means the bonding, mainly it explains about bonding in transition metal complex. Means it can separate metal and ligand. Up to now what we have spoken till valence bond theory, there will be bonding between metal and ligand. But here what we are speaking means in crystal field theory, there will be a bonding, but they will separate the metal and ligand complexes. Now let us enter into the crystal field theory. So generally this crystal field theory was developed by H. Beeth and it was modified by Van Welk. Okay, so this was developed by Beeth and modified by what here? Van Welk in 1935. So according to crystal field theory, what happens here? According to crystal field theory, there will be a bonding between central metal ion and ligand arises from purely electrostatic interactions. So means what? It depends upon repulsive and attractive forces. Okay, so here the ligand will be always the metal atom, central metal atom will be positive charge. The positive charge always will interact what here? Negative charge mainly. Okay, but the ligand consists of here negative charge and also neutral molecule. So this ligand which is containing negative charge and neutral molecule, in this we are going to take it as a point charges. So we are going to learn the third sem free electron theory. Okay, free electron theory means is nothing but what here? Free electron theory means the electrons is going to the positive charges, cations is going to revolve around the electrons like a C model. So the same way the positive charge is going to attract the negative charge by electrostatic attractive forces. Now, for example, here, if the ligand is an anion, okay, so if anion, what happens? It will attract towards the cation, which is a metal atom. Means what happens here? These are oppositely charged. Means if it is a anion, if it is a cation, these are oppositely charged particles. If the ligand is a neutral molecule, for example, here NH3, which is a neutral molecule, or H2O. So here the negative means this one we call it as ion dipole. Why? Because nitrogen will show partially negative charge, H will show partially positive charge. So these two will show dipole moment. Because of that reason, what we can say here, these neutral molecules in the same way H2O. If you take H is a partially positive, oxygen is a negative. So what happens here? They will act as a neutral molecule and ion dipole. If you take negative and positive, what happens here? There will be ion charged particle. Okay, so then what happens? The negative end of the dipole is attracted towards them. So somewhat here the nitrogen atom water, this is a negative end. Okay, so this whole molecule is dipole, ion dipole. So this negative end, whatever it is there, the nitrogen part will attract towards the positive atoms. Okay, so this is the meaning of this one. Means what here we are having d electrons also. Now, so there will be, what happens here? There will be a repulsion interaction between d electrons, which is present on the metal ion and the ligands. So means what here? As we are saying that d orbitals have same energy. D orbitals are divided into 5 orbitals which are having same energy. Okay, but there will be some repulsive forces, repulsive interaction between the d electrons. When you write the neutral molecule, small amount of negative charge is going to attract the positive charge. Means what? There will be some repulsion between them. So that one which is present on the metal atom and ligands which is going to present on d electrons. So this theory mainly describes the breaking of d orbital degeneracy due to presence of ligand. So because of the ligand, the same energy, d orbitals have same energy, that's why we call degeneracy. So when ligands are present, what happens? It is whether it will increase, whether or it will decrease. Means what? The degeneracy, the same energy will be lost. So here we have taken splitting of d orbitals, that is 5 d orbitals. If you have been seen here, dxy, dyz, dzx, these all are between the, these lobes are between the axis. Okay, so means what? These are not presenting on the axis if you have been observed these 3 orbitals. But coming to here, these two, dx square minus y square and dz square, these are presenting on the axis. These are not, these 3 orbitals are not presenting on the axis. Means what happens here? It will be having less energy and less repulsive forces. Why? Because these are not presenting on the axis. But coming to here, these two are presenting on the axis. So when they are presenting on the axis, what happens? There will be more repulsive forces. There will be less repulsive forces in these orbitals. So it mainly describes about the metal ligand bonds basing upon the strength. The energy of the system also changes, and also there will be change in magnetic properties and also column. When the energy changes, automatically magnetic properties will change and also color will change. So this is about, sorry for the disturbance. So this is about the d orbital crystal field theory, how they are splitted. So now the crystal field theory, orientation of d orbitals. So means for the splitting of d orbitals. So as I have told you, dxy, dyz, dzx. See here dxz. So these are line between x and y axis. Means they are not going to present on the axis. Okay, in between they are presenting. In the same way yz also in yz axis, and in the same way xz also they are present on the z axis. So means what happens here? They are present on the, they are not going to present on the axis, but there is an axis dx square minus y square and dz square. So these two, what happens? These two present on the axis. They are going to present in the axis. These 3 are not present on the axis, but these 2 are present on the axis. In dz square, you see there are 2 lobes on z axis, but definite donut shape we are having here. Okay, so which lie on the plane around the 2 lobes. So these are the splitting of the d orbitals. So now let us take one example here, that is octahedral complexes. So if you have been taken octahedral complex, there are 6 ligands which is attached to central metal atom. So this is a central metal atom. These are 6 ligands attached to central metal atom. So here when ligands approach the metal ion, when these ligands are donating, going to metal atom along the xyz axis, then what happens? The d orbitals is oriented. Means what happens? The dx square minus y square dz square will repel more, means by the ligands, while the dyz, dxz, dxy axis very less repulsion. when they approaching. Why they have more repulsive forces? Why these have less repulsive forces? Because these d orbitals, as I have told you, there are 5 d orbitals when we are not applying any ligand. When ligand, same energy it is going to have. When they approach the central metal atom, means when they are giving electrons to the central metal atom, automatically what happens? The energy will increase here. So whenever the energy is increasing, automatically it is divided into two types of sets. One is dx square minus y square and dz square. Another one is dyz dzx, which is having very less energy. So when ligands are approaching along the axis, automatically the degeneracy will decrease. In crystal field theory, the degeneracy should be removed. Okay, it will remove the degeneracy. Why? Because here we are going to separate. There will be interaction between ligand and metal. Okay, so whenever you are splitting these two types of energies, this splitting of energy levels we call it as crystal field splitting. Okay, the energy levels of d orbitals when we are splitting, that one we call it as crystal field splitting energy. So now this crystal field energy, the d orbitals is divided into Eg and 2Tg. So the energy gap between, so this is nothing but Eg, as you have seen, this is nothing but T2G. So this energy gap we call it as what here? Crystal field splitting energy. When it is splitted, it is crystal field splitting. So the energy gap we call it as what here? Crystal field splitting energy. It is denoted by, here we are speaking about octahedral complexes. Because of the octahedral complexes, it is divided into delta naught, denoted by delta naught, or 10 dq. Okay, so this delta represents what here? Crystal field splitting energy. So now let us see, we are applying some energy. So the 3d orbitals which is in free metal ion. Okay, so means what here? The ligand is not approaching here to the central metal atom. When ligand approaching the central metal atom, the energy is increased here. Okay, for example, here I have taken a spherical field metal. So these are the ligands which is having same energy. Spherical field is going to have the same energy. Okay, so when I increase, means when the ligands is going to the lone pair of electrons present on the ligands, when these are approaching to the central metal atom, which will show negative charge, so then automatically what happens? The energy is increasing. Even energy is increasing, there will be repulsive forces. So then what should happen? The degeneration should remove, but still it is having the degenerate d orbitals. Degenerate means what here? Same energy. Somewhat energy is there. So then afterwards what happens? It is going to split into two types of energy, that is Eg and T2G. Eg is having high repulsive forces and T2G is having less repulsive forces. Why? Because it is present between the axis, it is present along the axis. So here this one we call it as barycenter. What we can say? Barycenter. So this is having the energy gap, how much? Delta naught. So now to this barycenter to T2G orbitals, the value will be 0.4 delta naught. Why? Because less repulsive forces. If it is high repulsive forces, the value will be 0.6 delta naught. This is a high spin complex. This is a low spin complex. This is the splitting of d orbitals in octahedral crystal field theory. So now we are having crystal field stabilization energy. So what is crystal field stabilization energy? The energy difference between distribution of electrons in a particular crystal field and that all electrons in hypothetical spherical or uniform field levels we call crystal field stabilization energy. So means what here? Crystal field stabilization energy is nothing but here this is a hypothetical manner. Okay, this is a way the degeneracy is lost somewhat. So the electrons present in hypothetical, so there will be some energy difference between these two. That one we call it as what here? Crystal field stabilization energy. Okay, so this is T2Z, this is easy. If you take one electron, then we are going to get 1 into 0.4. Only lower part it enters. If you take D2, the electrons enter into only 2 orbitals. If you take D3, it enter into 3 orbitals. See here, it is not entering into EG orbital. Why? Because there are no electrons present over here. If you take 1, 2, 3, if one electron is present, 1 into 0. This energy what here? 0.40. If you take 2 electrons, D2, 2 into 0.4 delta naught. If you take 3 electrons, that will be 3 into 0.4 delta naught. Okay, so this is nothing. If you take D4 and D7, so metal ions with 4 to D electrons will exist as high spin, at the same way low spin. Weaker ligands is nothing but what here? Fluorine, chlorine, bromine, okay, oxygen, sulfur, these all will come under weaker ligands. So these ligands will give high spin complexes. Stronger ligands like cyanide, isocyanide, NC, CN, CO, okay, so and also we can say NH3. So these all will act as stronger ligands. This will give low spin complexes. Okay, so here the electrons require energy. Here the electron pair require what here? Energy. That one we call it as spin pairing energy. If the spin pairing energy is less than crystal field splitting energy, then the next electron will go to dxy, dyz, dzx orbitals due to stability. Why? Because it is a low spin complex. If it is greater than delta naught, the electron will go into dz. See here, for example, d1, d2, d3 we have seen. So means what happens? The energy is very less compared to delta naught. Then what happens here? Whenever the energy is very less compared to, so how we know that the energy is very less? See here. Here it is having 0.4, 0.8 and it is having 1.2. So means what here? We are having total 10 delta naught for octahedral. So if you compare this one to this, it is only 0.4 and it is only 0.8 and it is only 1.2. Then what happens? The electron will shift to dxy, dyz, dzx. If it is more than 10, it will going to splitting into EG orbital. That is the meaning of this one. Okay, let us see now D4 to D7. So D4 to D7. Okay, so when you take D4 to D7, the electrons is going to split like this. T2G3 EZ1. So this is T2G3 EZ1 according to Hund's rule. Or we can take it as T2G4 EZ0. Low spin means what we are going to get. High spin means what we are going to get. For high spin, how much value? 3 into 0.4 minus only one electron, 1 into 0.6. So if electron is entering here, then it is giving 0.6. If it is a low spin, we are going to get 1.60, 4 molecules. In the same way, D5, you are taking low spin complex, high spin complex. Low spin, we are having how many unpaired electrons here? Unpaired electrons, how many we are having? Total 5. 5 into 0.4. Sorry. 3 into 0.4, 2 into 0.6 minus. If it is a low spin, total 5 electrons we are going to take. Here 2 and here 0. And coming to here D6. D6 also same. 4 into, for D4 to D7. This is a high spin, this is for high spin, this is for low spin. 4 into 0.4 delta naught is for T2G And for Eg, 2 electrons is present, that's why we are writing 2 into minus 2 into 0.7. But for low spin, all the 6 electrons are present. Okay, and coming to D7, for high spin we are having 5 and 2, and for low spin, here you observe here after filling of electrons there will be 1 electron present on the high spin. So means what, here 6 electrons it is there and 1 electron is present on Eg. And from D8 to D10, if you have been seen here, D8, D9, D10 configuration, there is only one possible way, okay, for distributing electrons. So here electrons between T to G are easy orbitals. So here completely filled everywhere, T to G easy. And see here, this is the only possibility we are going to have in D8 and D9 and D10. Why? Because these are completely, here what happens, whether it is in low spin or in high spin, we are getting equal energy, D8, D9, D10. Why? Because in high spin 2 electrons, low spin also 2 electrons. In high spin 3 electrons, low spin also 3 electrons. Here 4, 4. So in all the cases, what happens? The electronic configuration involving 2 electrons in the same orbital. This is reduced by the energy pairing of electrons. So this is nothing but octahedral complexes for all d orbitals. In the next class, we can see tetrahedral complexes and square planar complexes. Thank you.